Okay, thank you very much. And I was talking about sources for this material. There are several research papers, and there is also an extensive computational study that has just been completed that can be found all from my website. It was just published with some of my collaborators at ASU, Stephanie Gill, who's now at Harvard, and her students, Sushmita Bhattacharya, Shiva Kailas, and Sahil Badial. And let me also mention this talk is going to be for 30 minutes, but there's an hour, 1 hour version of this talk that recorded recently and can be found at YouTube and it's accessible from my website in case you want to see more details. So here's my outline. I'm going to talk about multi-agent problems in general, then give a dynamic programming formulation for addressing them. Then the key part for this talk is a new type of policy iteration, which involves agent by agent policy improvement. And I'm going to talk about the exact version of this method and then an approximate version, which uses neural networks, value and policy networks. Then I'm going to talk about how to introduce autonomy into the algorithm so that the agents don't have to communicate as much. And then I'm going to talk about the multi-robot repair problem that I mentioned in the previous slide and give you some computational results. And I also have a video, and I hope it works. And I hope also that I will have enough time to do that. So let me talk about multi-agent problems. It is a very old and well-researched field. Dates from the 60s. It was not called multi-agent then, it was called team theory, decentralized control. It was a very active field, and it relates to a situation where you have multiple decision centers, what we call agents, and each one has its own decision variable, this views that you see here, and they collect information and exchange information from the environment or from each other. And at every time step, they apply a decision. Each agent applies a decision. Agent I applies decision UI sequentially in discrete time based on the information that's received. So what they do at time 0, they have some information. They apply the first decision, the first control. Then they collect information. And then at time 1, they apply a second control. And then new information again, a third control, and so on. So the discrete time system, but the characteristic is that the control or decision variable has multiple components, one per agent. Now this diagram here includes a very large collection of problems, and there's a major fundamental distinction between the different structures that can appear with the context of this problem. This was known back in the 60s, and one of the names that you will see referenced in connection with this is Witzenhausen, who wrote some fundamental papers about this distinction. And there are two structures. One is the classical information pattern, where the agents are fully cooperative, they fully share their information, and they never forget the information. And this is the case that's being treated, that can be treated by dynamic programming. This is the quote unquote easy case, although it's usually not that easy, but it's the easy case as compared to the other structure, which is the non-classical information pattern, where the agents do not have common information. And also they may be antagonistic, although we're going to talk about the cooperative case here. And this case is hard, very hard. And the reason is that in contrast to a classical information pattern, it cannot be treated by dynamic programming. There's no dynamic programming algorithm that can be used in connection with this non-classical information pattern. And this makes the problem very hard. And just to give you a personal sense of this, I have actually worked on this problem when I was a PhD student. That was 50 years ago. And I spent 6 months working quite intensively on this problem, and I gave up. And the reason was I realized the problem is so hard that I cannot possibly get a result that will be that will be strong, a strong result. So I gave up, worked on something else, but the field went on strong in the 70s. And then in the 80s, it sort of started losing steam because people were getting some theoretical results, but they could not, these results were not very applicable, particularly with the computers of the day. So the field stayed somewhat dormant up to about 15, 20 years ago, when reinforcement learning came along and introduced its own brand of algorithmic approximations. And the problem did not become any easier, but people were less afraid of it. Let's put it that way. We are going to start with the classical information pattern. However, we will introduce a framework that admits generalization to some extent to the non-classical information pattern. So remember here that the agents have exact state information, choose their controls as function of the state, and they share the same information. So conceptually, we can view this as being, as having some kind of a computational cloud that collects all the information from the environment, from the agents, and then beams back to the agents some state information, whatever they need to know in order to apply control. And we are going to assume a model that's standard in dynamic programming. It involves state X and control U. We're going to focus on discounted infinite horizon problems, which are stochastic. And the characteristic of this model, which sets it apart from general dynamic programming models, is that the control has multiple components, M components, each component corresponding to an agent. And agents here is just a conceptual metaphor. The important mathematical structure is the multi-component structure. These components may correspond to multiple robots going around the field doing things, or they may just be a single robot having M arms that are controlled individually by these U components. And our theoretical framework is dynamic programming. This is the nice consequence of having a classical information pattern. And our initial aim is going to be very simple. We're going to aim at faster computation. We have a difficult problem. We're going to try to make the computation go faster. And one of the issues we're going to deal with is the exponential size of the search space. Here we have multiple components, so the size of the number of controls grows exponentially with a number of agents. This can introduce prohibited computation in many types of dynamic programming operations, including minimization of the Bellman equation. The second issue that we're going to address is an issue of autonomy. We want to have the agents' computer controls in parallel so that we gain by parallelization, gain a speed up. And in the process, we're going to deal in part with the non-classical information patterns. So that's where we are going. And let me give you an example of a problem of this type. It's representative of many types of problems, like multi-robot delivery problems, multi-robot maintenance, search and rescue, firefighting, and so on. But to make it more interesting, we're going to introduce in terms of spiders and flies. So what we have here is 15 spiders. They move in the 4 directions on a grid, or they can stay where they are. And they have perfect vision. In other words, they know where all the other spiders are. And they also know where the flies are. There are some flies here, which are passive and blind, and they just move randomly. They don't do anything purposely. And the objective is to catch the flies in minimum time. So now the size of the control space, each of these spiders has 5 choices, have 5 motion choices, and there are 15 of them. So the number of joint possible moves at any one stage is 5 to the 15. It's an enormous number. And so in terms of Q learning, this means 5 to the 15 Q factors at a given state to compare. What we are going to do is reduce this from 5 to the 15 to 5 times 15, while still maintaining good properties in the context of policy, iteration, and other dynamic programming related algorithms. And the idea is to break down the control into a sequence of one spider at a time moves. So within this context, we introduce an order of the flies, of these spiders, and the first spider makes its move and broadcasts this move to all the other spiders. The second spider now makes its move, taking into account the move of the first spider, and then after it selects the move, broadcasts this move to the other spiders. And we go through this 15 times, one spider at a time. So the total number of comparisons that we have to make for this is 15 spiders, 5 comparisons a piece, so it's 5 to the 15. Now, in this process, there is serial computation involved because the spiders select their moves one at a time. We would like, ideally, to give some autonomy to the spiders. So what we're going to do is introduce some coordination information that will play the role of communicating and broadcasting the spider moves. This can be viewed as signaling, which is pre-computed, and it's going to be available possibly through neural networks, so that the 15 spiders will choose moves in parallel, which gives us an extra speed-up factor of 15. I'm going to come back to this problem of spiders and flies later. So let me now introduce the dynamic programming formulation. In this talk, I'm going to focus on finite-state infinite horizon problems with discounting. So we have a system, a discrete time system, which has state xk, control uk, and there's a random parameter, wk. And we move from an initial state x0 to a sequence of states from xk to xk plus 1 using this system equation. And there is a random cost associated with transition that involves also a discount factor, alpha to the k at the k stage. And we're interested in policies which are multi-component, okay? The control has m components, and we want to find a policy which is m functions that map the state x to the control components that must satisfy some constraint. And given a policy mu, we accumulate the cost over an infinite number of stages, take the limit as the number goes to infinity, and we obtain the cost of a policy at a given initial state. So this is the cost function of the policy of a policy mu, J mu. And we want to find the optimal cost function, which I'm denoting here by J star. And the fundamental result here revolves around Bellman's equation. The right-hand side of Bellman's equation is this expression, minimization overall controls of the Q factor corresponding to all the Q factors, over all the Q factors corresponding to a state X. And if we do that with J star being here, then we obtain an optimal policy. So this is a fundamental results, very nice, but there are some problems with it. We need to know J star, which is extremely hard to find. In fact, the whole object of reinforcement learning is how to make approximations to J star that are sort of adequate. But there's a second difficulty here. We minimize overall possible controls. And remember, the search space grows exponentially with a number of agents. So this minimization is also a difficulty. So staying again with the exact version of this problem, let's talk about policy iteration. Policy iteration generates a sequence of policies starting from a given policy, which I'm going to call base policy, mu. We evaluate it, compute its cost function, and then we improve it by minimizing in Bellman's equation, but with J mu replacing J star. This is a minimization that's possible to do because if necessary, we can calculate J mu by simulation. And if we do this minimization for every state, we obtain a new policy, which I'm calling the rollout policy. So that's the definition of the rollout policy. We have the base policy mu, we evaluate J mu, and then we improve it by minimizing in this expression, this expected value over W. And the fundamental policy improvement property is that the rollout policy is uniformly better than the base policy. Okay, the term rollout, the term was initially introduced by Tesoro in the context of backgammon in the mid-90s. In the context, in exactly the same context as I am discussing here, as the new policy generated by policy improvement on a base policy. Now, the term rollout has been used in many other different ways in the literature. For this talk, the rollout algorithm is simply one iteration of the standard policy iteration algorithm. And instead of going through this many times, we go through this only once using some base policy. And it can be implemented online if these values of J mu are available, perhaps approximately through simulation, perhaps in conjunction with a neural network. And rollout has another important advantage in addition to policy improvement. It has it is robust with respect to runtime modeling uncertainty. In other words, even though we have a certain model, that model may change. The real system may change over time, and we may record these changes and encode them in this simulation field, calculation of expected value. So even though mu does not change, the rollout policy takes into account the changes of the in the model and implements online replanning. That's an important advantage, and not all methods have this advantage. So now let me give you an outline of our approach for multi-agent problems. We start with a classical information pattern, and we're going to propose a new type of policy iteration method that involves this new form of policy improvement with one agent at a time minimizing. It uses a sequence of single component minimization and intermediate agent coordination in the sense that the agents compute their controls and then they communicate them or make them available to the other agents who take them into account when they compute their own controls. And we will view rollout, as in the previous slide, as a single online policy improvement. Starting from a base policy, we compute a rollout policy based on one agent at a time minimization. And the base policy can be computed a number of different ways. A different method can be used to compute the base policy, the policy gradient method or a random search method. And this is precisely the approach that's being used in AlphaZero. Generate a sequence of policies, and online, when you play, you use rollout. There is the only difference is that there are no multiple agents in AlphaZero, and also instead of one at a time, one agent at a time simplification, it uses Monte Carlo tree search. But it's basically a policy iteration method with an online rollout. Now, how do we go from the classical information pattern to the non-classical information pattern? Basically, we are missing information in the non-classical information pattern. So instead, we use guesses and we treat them as being exact. The guesses can be pre-computed. They may be policies, for example, signaling policies, I called them earlier, and they can be computed possibly through neural network training. And there is a lot of research in this area, and I'm going to give you an idea of what we have done in the context of the case study that I mentioned earlier. Okay, so let me go into details about this new type of policy improvement. The standard rollout algorithm, given the base policy mu, evaluates J mu and minimizes over all possible controls, over all possible m tuples of controls. In this equation, finds the minimal Q factor, but the problem is that the number of Q factors grows exponentially with the number of agents. And the proposed alternative, which I'll call multi-agent rollout or multi-agent policy variation, is to, instead of this minimization over all components simultaneously, do them one at a time. So we have this base policy, and the first agent chooses a control by minimizing over its own local controls while setting the controls of the other agents to the base policy. Now, given the control of the first agent, we use it to compute the control of the second agent, who minimizes over its own controls the corresponding Q factors, setting all the controls of the future agents to the base policy, but the rollout control of the first agent, which has already been computed. So we go in this way for m steps, going through all the agents. And now when we calculate the number of Q factors that we have to compute, it is linear in m, because it's a certain number per agent, and we do this m times. So there's an enormous speed up relative to the standard rollout. And that's what we're trying to take advantage of. Now, what's the theory for this? It turns out that there is theory, and the theory is quite old. There's a whole section in my neurodynamic programming book from 1996 with John Tsiklis, which deals with how you trade off complexity of the control space with complexity of the state space. In particular, we do the following trick. We take a stage that generates xk to xk plus 1, and we unfold the control action one component at a time. So we introduce intermediate states here. First apply the first control, go to this state, then the second control to this state, and so on. And at the very last choice of control, we make the transition to xk plus 1 using this equation and the corresponding cost. So what we have here is a problem with m times more stages, m times more cost functions, because we have introduced extra states and their corresponding cost functions. However, the controls are taken over a much simpler space. On the other hand, when you do rollout, you don't care about the size of the state space at all, because at each stage, you're at a single state, and you don't care where the other states are and how many they are. You only look at a single state. So the fact that we have made the state space more complicated does not bother rollout at all. And the key theoretical fact is that with this equivalent problem formulation, the cost improvement property is maintained. And why is that? Because if you think about it, the one agent at the time rollout algorithm that I gave in the previous slide is just the standard rollout algorithm for this reformulated problem. Since this reformulated problem is equivalent to the original, when you improve its cost, it's the same as improving the cost of the original problem. Hence, we obtain this cost improvement property. And as I noted earlier, there's a tremendous complexity reduction. The one-step look-ahead branching factor of the standard rollout algorithm is reduced from exponential to linear, where n yields a number of possible choices for each of the components. Okay, so that's the theoretical idea, and you can build a lot of algorithms around this reformulated problem. Now, I want to give you an illustration of these two different forms of rollout with the video, and I hope this will work. Okay. So here, what we have is two spiders, 4 spiders and 2 flies. Can you see that?
Yes.
Oh,
yes, we can. I can.
Okay, good. Yeah. So I'm going to show you first the standard rollout algorithm. There are the 4 spiders here, they're in the center. The base policy here is a greedy policy, a shortest path type of policy, whereby the spiders go straight towards the closest fly. They figure out what is the closest fly, and they go to that. Each one goes to its closest fly, and they keep going like that. They don't coordinate. That's the main thing. They don't coordinate their choices. So in this particular case, where they start out with at the same location, they will all go to the same fly because they see this as their best target, and they don't coordinate. Ideally, however, what you would like to see is that 2 of the spiders are going to go towards one fly, and the other 2 are going to go towards the other fly. And also, if they're really smart, they may try to encircle it, because these flies move randomly, and it makes sense to try to encircle them. So let me show you what the base policy does. Okay, so they all move simultaneously. Now, they go to the closest fly using the Manhattan distance metric. So 2 of them prefer the horizontal in case of a tie, and 2 prefer the vertical. So that's why you see them split off and moving inward. So now they've caught the first fly right here, and they start moving on towards the second fly. No coordination here. So I'm going to stop it because it's going to take some time. I'm going to give you the results later. Now let's see what the standard rollout will do. Okay. Now, immediately you see that standard rollout introduces some intelligence into the scheme, whereby they split off and they go and chase different flies. And they also try to do some form of encirclement, which will come out from the algorithm. Much better results. And I'm going to go also into the agent by agent rollout. The results are pretty much the same. Agent by agent rollout does roughly the same things, although not quite exactly the same. Again, the spiders split off and they go towards, try to encircle the flies and so on. So the summary of the results, okay, the time to catch the flies, the base policy takes 85 steps. The standard rollout takes only 34 steps. However, at every move, at every time step, it has to compare an exponential number of choices, 625 move choices. Agent by agent rollout, again, has the same performance, but requires only 20 move choices. So there's some substantial gain here. And I'm going to show another video later that illustrates the same thing as well. Okay, so now we have the standard rollout and the multi-agent rollout, and how do they compare? They produce different rollout policies, different sequences in the context of policy iteration. And one policy may be better than the other. There's no clear domination of one method over the other. However, the standard rollout requires exponential search, intractable computation, even for a modest number of agents. And in our computational experiments, we find that agent by agent rollout, it performs about as well as standard rollout. And And it appears that for many types of problems, this is true, but there is no definitive result that will establish this one way or the other. Okay, so this has to do with rollout.
Sorry to interrupt, only a few more minutes, I think.
How many minutes?
Well, I mean, we're just about at the end now, so just a few minutes.
We're about -7. I guess if you could wrap up.
We started a bit late. But,
wonderful.
Okay, I think I'm going to,
So half an hour goes so quickly.
yeah, definitely. I'm sorry about that. This talk came from a 1 hour talk. It was trimmed down to half an hour, but not quite enough. Okay, so we're in this topic of comparing standard and multi-agent rollout. And how about multi-agent policy iteration? It's the same type of policy iteration, but use agent by agent policy improvement. And it doesn't terminate with an optimal policy. Instead, it terminates with an agent by agent optimal policy, which is a Nash equilibrium. If you view the agents as players, with each having the same cost function. And a Nash equilibrium need not be optimal. There is a convergence result, which establishes, for exact policy iteration, establishes finite convergence. And I have no results for rate of convergence, but let me go quickly through the use of approximations. All of the preceding discussion was for exact policy iteration and exact rollout. To introduce approximations, we have to introduce an approximation to in the evaluation step of policy iteration, and we do this by using some kind of a value or critic network, neural network, some other architecture, collecting value data from the base policy through simulation and fitting a neural network or some other architecture, computing rollout controls and fitting a policy network to those, and that's how we obtain an approximate rollout policy. And then, of course, we don't have exact policy improvement, we have approximate policy improvement with respect to some agent. If we do this once, then we obtain an approximate form of rollout. If we do this repeatedly, then we obtain an approximate form of multiple of policy iteration. And now, if you want to do policy iteration, it can only be done with offline training because you can't train neural networks online. So rollout can be implemented as an online algorithm, but approximate policy iteration cannot. And incidentally, AlphaZero uses a scheme of this type, offline policy iteration plus online rollout. So now I'm going to spend just a little time.
So sorry, we have to cut it off there because it's
the next sorry about that.
I'm so sorry, but everyone, I really encourage you to ask questions in the chat messages or to follow up via email. I'm sorry that we don't have additional time.
Okay, so I want to give just a couple of bullets from this concluding slide. Is that permissible?
Of course.
Okay, so our methods require the classical information pattern. However, they can be the basis for extensions to the non-classical information pattern through this idea of pre-computed signaling policies that I haven't talked about, but you can read about. And now I want to say something about comparison with existing methods. In our computational study, which involves a very challenging POM-DP problem, we have also applied existing methods. And these are POM-CP and DESPOT. These are general POM-DP type methods involving long look ahead, but no rollout. Long look ahead with pruning or Monte Carlo tree search. DESPOT, these methods are not well suited for multiple agents. DESPOT gave up at 4 agents, could not solve problems with 4 agents. POM-CP was able to solve problems with 4 agents, no more than 4 agents, but it gave results that were worse, often worse than the base policy. MAD-PG is a different type of method based on policy gradient ideas, and it is applied. It applies to multi-agent problems. MAD-PG just could not cope at all with our problem. It was just doing very strange things. We worked very hard to make it work, but it simply would not work and would give you much worse results than the base policy. We contacted the authors of MAD-PG to see what may be going wrong, but in all indications, MAD-PG cannot solve this type of multi-robot repair problems. And not only that, it doesn't do sensible things at all. I'll leave you with that, and you can read the computational results from the paper that's posted on my website. And I welcome your questions. I'm sorry about the taking over.
Thank you so much for that talk. And I think one thing I know, it's always personally frustrating when I don't have enough time to share some of the results I'm excited about. So if you wouldn't mind, if you have a link to the longer talk, if it's been pre-recorded, we could put that in the chat messages, and that will also give a nice pointer to people who can see the full version, because we can make sure all the attendees see that too.
Yeah, everything is at my website, and if one goes at my website, which they should have no difficulty, there's a link to the new book and also to my earlier book on reinforcement learning, and everything is very clearly given there, all the papers, including and the YouTube 1 hour talk.
That's wonderful.